Bismillahirrahmanirrahim. Assalamualaikum, salam sejahtera and very good morning everyone. Welcome to the ISN lecture series of the year 2021. Thank you for being here this morning. My name is Muhammad Fauzi bin Ibrahim and I will be your host for today's program. Today we are pleased to welcome TS Dr. Muhammad Najib bin Jamaluddin, a very special speaker from Sports Innovation and Technology Center, Institute of Human Centered Engineering, Universiti Teknologi Malaysia, Skudai, Johor. He is a researcher in UTM whose passion has brought him to venture the application of electronics and systems into the field of biomedical engineering and sports technology. Together with his team, several research works have been focused on, especially for measurement of psychological signal for man in motion. He also leading project for integrating biomedical and sports application into the domain of fourth industrial revolution. His expertise and experience spans from capturing signal from the human body to analysis of signal using cutting-edge machine learning technology. And today, Dr. Najib will be sharing his expert on IMU sensors in sport motion. With that, I ask that you give your full attention to Dr. Najib and help me in welcoming him to the platform. Okay, Dr. Najib, you may begin now. This session is yours. Okay.
All right, thank you, Muhammad Fauzi Ibrahim, for the introduction. So, Assalamualaikum and good morning everyone, participants for this Perform lecture series by ISN. So, I understand that this is Series 5 for this year, 2021. Right, so my presentation, or should I say discussion, so would be on the topic for the IMU sensors in sports motion. Right, as we know, in sports, in sports athletes, motion is the basic, the element of sports sports. So everything is motion, right? What we can say is that in sports, a major field in the research of sports is biomechanics So to be more specific, it is biomechanics. But however, we will look and we will see how IMU sensors can be fit in into biomechanics, or should I say in general sports motion. Right? I don't use the term biomechanics because biomechanics, I would say it would go specific into the total, the entire mechanics of the human, of the athlete. But what I'm discussing for this topic here today, I'm applying. We are looking at the application of sensors, not only on biomechanics, but also includes the tools or the equipments, sports equipments, or other than the biomechanics itself. So it's quite a general topic. So biomechanics is more specific, but I'm touching on a little bit more general. Right? So to go forward, let's look at what's the button here. Okay. So these are some outlines. I might not be presenting all, and also it might not be in that order, right? I've put there some slides on demonstration videos, but unfortunately I did not manage to compile the videos for specific meanings. I do have videos, but it's not fully compiled yet to deliver some message. Right, but these are some outlines that I will share with you throughout this 1 hour of this lecture series. So we will look at some fundamentals of IMU, and then some research applications, challenges, especially validity, some pros and cons. We will look at some specifications, and also processings and analysis. Right, so I hope you are ready to listen and watch, and please do take down notes if you have any questions, and you can put them in the chat box. Okay, some fundamentals of IMU. So IMU, in terms of definition, it is the abbreviation for inertia motion unit, right? Inertia motion unit. So it's the term. The keyword there is actually inertia. Inertia. So inertia means an object which has in a momentum. So when there is changes in momentum, right? So some changes can be happen. So that would be in the knowledge domain of physics lah. So inertia. So basically, these sensors are very. We can find these sensors of IMU already in most of our gadgets nowadays. Especially your smartphones, your iPhones, Androids. I would say almost all types of phone now have these IMU sensors, right? So compared to the early years of smartphones, let's say during around I think maybe 2012 or 2016. So not all phones have these motion sensors, but now almost all have. Almost all have. At least if you can observe from your phone, when you tilt your screen, when you tilt from landscape to portrait, then it changes the orientation. All right. So that means your smartphone have these IMU sensors, inertial motion unit sensors. So basically, there is three main measurements of this sensor, the IMU. The first one is accelerometer, the second is gyroscope, and the third one is magnetometer. Right? So these IMU sensors might not consist all of this, but all IMU sensors will consist at least the accelerometer. Alright, so accelerometer is a measurement device which measures the acceleration. So acceleration, if we still remember our physics, alright, acceleration is the velocity over time. Velocity over time. So which means that velocity is usually we term it as the speed lah. The term that we use is speed. So it's, if we drive a car, there will be in kilometer per hour, right? But as in a smaller scale, like these sensors, it will be in the scale of meter per second. Meter per second. So meter per second is speed. So acceleration means the changes of speed over time, or the rate of speed change. The rate of speed change. So so when there's speed change, that's an acceleration. If you have we call it no change of speed, if your speed is constant, then the acceleration is zero, right? So there's no, if you drive a car at a constant speed of 110, then there is no acceleration. But when you want to overtake a car, right, for example, from 110 kilometer per hour, you want to increase your speed to become maybe 140 so that you can overtake some lorries or cars, then you consider accelerating, right? That will be increasing speed lah. So when you want to brake, when you want to slow down, that is also acceleration. So that will be negative acceleration. So basically, if you a little bit on some equations lah, if you look at the equations below the accelerometer over there is basically the the differentiation, the double differentiation of x over dt, dt. So this is the maths lah. The maths, usually we do this maths during our secondary school years, right? But I'm not focusing on any mathematics today, so that we are discussing on the applications mostly, right? But what we can see, basically we will see the XYZ, the XYZ. So the Z would be the one in red, right? In red, the Z is a vertical axis. the blue arrows, then line would be the X, and the Y would be the green. So that is for acceleration. So speed, I mean the change of speed in a direction, right? So another application of acceleration is as simple as, you know, dropping an object. Let's say you have an object, and then you drop that, right? You have an object, it drops. So the acceleration of the object dropping would be 10 meter per second, right? Okay, so because that's the gravity, the acceleration of the gravity pulling down the objects, right? That would be the simple example that we can think of lah. Right, and then the second parameter for IMU is the gyroscope. So every IMU have accelerometer, but not all have gyroscope. But mostly would have gyroscope, especially if you can if your smartphone can open up the let's say YouTube, and then let's say for example if you open up a YouTube which have the 360 recording, right? Videos of YouTube with 360 recording, and also the using the virtual reality headset. Usually they have two screens. When you open up the YouTube, they have two screens, and then it says there 360, right? And then when you turn your smartphone device, and then you can see different aspects of the environment around that camera. So that if your phone can work that way, then it has gyroscope, right? But some lower grade phones do not have gyroscope, right? But mostly would have now. I think the direction would be that way now. Most would have gyroscopes. And then lastly is the magnetometer. This is very, very seldom. Only few phones you can find magnetometer. So with this magnetometer, actually you can find the direction of, let's say, the magnetic compass. If you want to find the Qiblat, or actually it should be available in most phones too. Actually, should be, right? Because if you want to use your GPS when you're driving, like Google Map, you should have magnetometer. But sometimes if your phone don't have, they have an algorithm which will calculate your direction of movement, but from 2 points. But seldom phones have this magnetometer. So basically the basics of this sensor is three of these, right? And then from these three sensors, you can measure, you can apply this to the motion in sports. Just now we talked about accelerometer, which is the change of speed in these 3D directions, X, Y, and Z. And then gyroscope. So what is the measurement of gyroscope? Gyroscope is the measurement of the rotation, right? Let's say you have an object, and then the object rotates. So the speed of rotation, right? So that is the gyroscope. So you can measure the speed of rotation around the z-axis, around the x-axis, and also the y-axis. So the rotation speed, right? So any object which rotates, you can measure through the measurements of gyroscope. Okay, why actually we need a magnetometer in IMU, right? It's actually related to the stability of measurements. We will talk about stability later. Due to the Earth magnetic field. So our Earth has magnetic fields, and these sensors are actually very, very tiny. You will see why this IMU sensors is actually quite sensitive to the Earth magnetic field. Okay, so let's go next. First of all, basically, what's inside the sensor? What is inside the sensor that makes it work? So it's like you have a platform, right? If you can see on the left over there, there's a platform, and then you have like a stand over there, and then some weights, some weights. So when you move the platform, right? When you move the platform, because we call it the stand, the pole is flexible. It's made to be flexible, and then you have a weight at the top. So when the platform below moves, and then the weight at the above will also move. So and then the movement of this setup will you can get some measurements of acceleration, right? So it moves. It's like a pendulum, right? So the same also goes to gravity, If so, the same setup, it goes down, you make it fall to the ground, and then actually you can see some changes, of the black, we call it the black ball in this slide. It will change. It will oscillate around the axis of the platform. So that is the we call it the mechanics of the sensor itself, right? So that is the block diagram, call it the block diagram. And then this is the design of the layout design of the sensor. So you have some stationary comb, something like this, and then you have a move on the left. You have a comb which can move, right? And then you have some flexible structure, which whereby the movable comb can move and oscillate around the, we call it the main axis, the main platform over here. And then from the movement because the stationary comb and the movable comb, when you apply voltage, actually is a setup of capacitor. So this is very technical, very sorry, but just to introduce first, we need to know first. Okay, so these changes of distance between these two surfaces which contain electrical voltage will provide measurements of capacitance, and therefore you will get changes, So the movement of the movable comb is translated into voltage, right? And then from the voltage, you read the voltage, and then you will through some programming technical engineering methods, you will need to change back to measurements of acceleration, right? But let's look inside. What is inside? Okay, just now is the layout, the layout design, and now what you're seeing here is the actual MEMS for the IMU. So it's very, very tiny. So you can see the physical structure inside the sensor, right? So some parts is fixed, and some parts of the comb is actually movable, right? But then now comes the question: how big is it? How big is it? It's actually very, very, very tiny. Right? So just a close up. Right? So this is this structure is you call it is fabricated, manufactured, very precise. Right? With according to our technology now, so everything is precise. It's very you call it surprisingly accurate and very precise. And it would be a waste if we did not use this technology for motion in sports. So that's a close up. Okay, what's the size? So you can see here, there's a scale in this slide over here. Okay, the scales, the lines, the white line below is shows a scale of 10 micrometer. So that's very, very tiny, right? Very, very tiny. And actually, you can. This is for one direction only. Let's say this is for X. So this is for X only. And then if there is other parts of this chip is designed and placed for the measurement of the Z axis, and then also the Z and the Y axis, the vertical, and also the horizontal axis. So these are very, very, very tiny. Right, which means that because this is very, very tiny, and therefore this is a very, very sensitive sensor. So which means that even tiny movements, this sensor can be able to detect. And because this is very, very small and tiny, and like I said just now, the electromagnetic wave of the Earth field can actually affect. Like if we refer to our physics during our school years, if you have it's either one way or the other. It's the Lenz's law. The Lenz's law. If you have a current through a wire, right, it will produce a magnetic field around the wire, right? Whereas if the other way around, if you have an electromagnetic field around a wire, you can produce a current flowing. So that's the other way around. So that's the generator, right? The concept of generator. How electromagnetic fields can generate electricity currents flowing through a wire. So these things can happen. The phenomena can happen to this sensor also, whereby the Earth's magnetic field can influence the currents flowing through these sensors. Therefore, usually to have a good sensor for IMU, it is best to include the magnetometer so that the measurements of the Earth's magnetic field is included into the calculation, so that the calculation will cancel off. In terms of the calculation, will cancel off the effects of the Earth's magnetic field. And then you can get the actual measurement or more accurate measurement from the IMU. Right. So this is very, very technical, right? But we need to actually understand. So we will see why. Is it viable or not to apply the IMU sensors in sports or in sports training, right? And then I would like to also highlight some sensors. They are sold as 2Ds, which means they have only X and Y axis, right? So for 2D sensors, it is most suitable for if you have a structure which is already fixed, right? Let's say the Z is fixed. The Z is fixed. You have the X, Y, Z, right? 3D. So the Z is fixed. Maybe you have a structure holding something. Maybe it's a robot, maybe, right? And then, but one part of the robot or you have a robotic arm is free to move, right? Either in X or in Y. So for that situation, for robotic, with a fixed, we call it fixed third axis. So it is okay. It is good for if you use the 2D IMU sensors. But for the human motions, the human motions is actually very complex. Even though you have the same skeletal structure as a human. But still, my moving gait and your moving gait might be different. If let's say if I were to run at my faster speed and you running at your faster speed, so the motion, the 3D motion will be different. So usually, if you want to apply for the measurement of motion, using IMU in sports, we use those 3D sensors, which provide the X, Y, and Z axis, right? Just to inform, there is such sensors that have 2 axes and not 3, right? Okay, so these sensors, because they move, these sensors is very, very sensitive. And also due to the the placement of the sensors, so it is actually not quite accurate. Not quite. I will not say accurate. It will not be accurate on its own, right? It will not be accurate on its own. Usually, when we want to apply these IMU sensors, we need to calibrate these sensors with the optoelectronic motion capture system, right? Usually, like centers like in UTM, Sports Innovation Technology Center, we have this Vicon motion capture system with 6 cameras, and I've seen also the same system in ISN. I think with more cameras, I think 12 or 16 cameras, right? So the more accurate measurement of motion is when you are using these cameras, right? Because when you are using this motion capture system with those markers on your joints, on your knees, on your limbs, so these multiple cameras will capture 6 cameras. Let's say in UTM over here we have 6 cameras, and ISN I think we have more than 6 cameras, maybe 10, maybe 12, right? So more cameras means you have more. It is more accurate because 6 cameras are observing specific points, specific points from the markers. Therefore, I would say that the most accurate, usually this has already been validated by research. The most accurate system to detect motion is via using the infrared or the optoelectronic motion capture system, right? But the thing here is when we want to apply another type of sensor, which is the IMU motion sensor. So because of its high sensitivity and also the measurements can deviate over time due to the magnetic field, like I mentioned just now, right? So it is best if this IMU sensors is to be calibrated against the motion capture system first before further measurements from the IMU I made, right? Okay. So these sensors need to be calibrated together, which means that, let's say, for example, you have your let's just use the name Vicon, because the name Vicon is usually very synonym to motion capture system, the brand Vicon. Let's say you have the Vicon, you have the markers over here, right? So of course you have your markers at points at certain parts of your body. So how do you calibrate? So at the same spot over here, you can put your IMU sensor also, right? You can put your IMU sensor. I would like to show. This is one sample from my from our lab over here. IMU sensor. This is the enclosure. You can just put over here and put along together with the Vicon markers, biomarkers, right? Put at the same spot, and then you record your motion, and then you get the measurements from Vicon, you get the measurements from IMU, and then you calibrate your measurements of IMU against the measurements of Vicon. This is the sensor. I mean the whole enclosure, and this is what's inside. What's inside. So this board over here, our team over here developed this in-house lah. So it's very, very small. So we are planning to make it much more smaller, so that it can be made wearable. So okay, full set body markers, and then okay. Usually when we are using the Vicon motion capture system, usually the purpose is to capture the whole, the human, the entire human body frame, right? From the neck, from the head, and then your shoulder, your torso, right? And then your limbs, your hand, and then your legs, right? Everything, basically everything. So in one aspect, actually, you can plan. Actually, you can set up by having several of these IMU sensors, and you put it on every part of your body lah. Your neck, your torso, your limbs, your upper limb, your upper arm, lower arm, upper leg, lower leg, right? You can put as much as possible. And then you can get measurements from them lah. And then the most important thing is to calibrate against the motion capture system. Okay, so but still research has been going on regarding the accuracy we need several algorithms, especially filtering, to improve the measurements so that there are, I think, at least 4 methods to filter those measurements from IMU, so that it is comparable to the Vicon motion capture system, right? But again, like I said, even though it is initially calibrated, at some other time when you want to have another recording, so you need to calibrate again, because the Earth's magnetic field is not always the same at the same place. It is always changing over time. All right. So when you calibrate against the motion capture system, this setup is able to measure joint angles, right? And then from these joint angles, you can compare relative rotations of the body frames. So let's say you want to do some measurements of cycling. You want to measure the knee angles. You want to measure the lean angle, your body lean angle, things like that. So yes, you can use this accelerometer, but you need to do calibration. All right. Usually, like I said just now, the Vicon motion capture system is the golden standard. So then the question is, why do we want to use accelerometer when why you want to use the IMU when you have the Vicon motion capture system, right? When you use the Vicon motion capture system, you are restricted in a lab, right? In our lab in UTM, it's quite small. I think at least it is 20 by 20 meters. The space around with the cameras around. I've seen in ISN it is much more bigger. So in ISN with more cameras, you can actually move more freely. But then still, why we need IMU when we have Vicon motion capture system, right? But so by having the IMU, right, when we apply this to the limbs, to the body, we can do these measurements out of the lab, right? We can use these measurements. We can do measurements of motions out of the lab without the very the high technology, the high end setup of the Vicon motion capture system, right? So you can go out of the lab, all right? You can go to the field. You can go to badminton court. You can go. You can apply to many other setups. So the lab, the motion capture lab, might be suitably set up for certain activities. Maybe let's say for badminton or cycling, or for some treadmill, right? But what happens if you want to go more than that? You want to go further than that. You want to apply to in other sports. Let's say you want to apply for we call it diving. You want to apply for diving. You want to apply for swimming, right? You want to see what happens when you want to when you do rowing, for example. So everything is outside. So with these IMU sensors, you can do that. But still, it is best to calibrate first. So the thing here is, if we focus, so usually for, like I said just now, about biomechanics, when we talk about sports, is our main domain of research would be biomechanics. So when we talk about biomechanics, we are talking about the body frames and the human body frames. So usually we do that with Vicon lah. Okay. So the thing is, when I talk about IMU sensors for motion, sports in motion in sports, so it's not only about the human body frames. we are talking also about, let's say, if you want to apply this to the rackets, or to the rowing oar, or to apply this to the bicycle. When you ride the bicycle, right? Maybe you want to speed up. What happens? What do you do to your bicycle? You want to see that, right? So you can do more. You can actually do more with IMU. So, but let's say you want to measure other than body frames, then we cannot calibrate lah. We cannot calibrate with the Vicon motion capture system using the standard body frames. Okay. Okay, and then we also do have challenges lah when we use the IMU sensors. So this IMU sensors, because it is placed on our tissues, our skins, on our muscles. Whereas when we construct the body frame for the Vicon motion capture system, it's actually like based on because our body is our core is our skeletons. So whereas our skeletons are wrapped by those muscles and tissues. So the thing here is we are not putting our sensors on skeletons. The actual, I mean the original measurements of the human body frame is based on skeletons actually. But the thing here, we cannot put sensors on our skeletons. We have to put them on the surfaces of our arms, our skin, our muscles. And these tissues is soft, so it can move around. Even though you stick your sensor on your skin, so when you move, you do some flexion, things like that, and then actually it will also move, so it doesn't stick to the skeleton. So this is among the main changes lah. Among the main challenges to measure the the motions of the human body frames for both IMU and using both. This soft tissue effects is actually is a problem to the both IMU and the motion capture system, right? And then challenges related to the IMU is related to the like I said just now, the calibration. So when you do calibration, you need to do two types of calibration. The first is static calibration, and also the second is dynamic calibration. So you need to find the accuracy and see what is the error, right? So both of these will always be a challenge every time you make a recording and for you to do the analysis. So these challenges is actually very, we call it, is usually specific. I would say specific if you are talking about motion, biomechanic motions, specific to the human body frame. Let's say you want to know how much your knee bend, how much your arm, your angle, your elbow bends, and your angle. So if you're looking at that, if you are measuring these human body frames, then this would be the common challenges that you will face when you do measurement. All right, but however, that's not always the case. When we talk about motion, it's not always about measuring the human body frames. We can also talk. We can also measure specific parts of the body only. Let's say you want to measure your knee only. I mean your leg only, or your step. You can place this in your shoes, so you can measure that. You can measure motions from your feet when you run, things like that. Right. The pros and cons of using these IMU sensors is you can use for outdoor recordings because it is not based on optical measurements like the Vicon, motion capture system. It is based on the the infrared cameras. Therefore, you have to set up in a enclosed room. You cannot expose to sunlight. Usually when you do sports training, you do it outside, and outside is usually exposed to sunlight. So IMU is good for you if you want to use outdoor, and you can use even with sunlight. You can do it anywhere, so you can do it in unconstrained space. Right? Some people say that mention that the IMU is a measurement of biomechanics in the wild, so it's just you can do it freely. And you can also measure the full swing without additional hardware. Let's say, for example, for the vehicle motion capture system, right? If you have, let's say, 4 cameras, right? 4 cameras, so only 4 cameras are viewing your biomarkers. So there are points when your biomarkers are blocked by some parts of your body, or your legs, or your arms. So that camera does not capture. So which means that if you want to record a full swing using the vehicle motion capture system, you need more cameras, right? So when there are parts of your body blocking the biomarkers, other cameras from the other angles can capture the biomarker position, right? But with IMU, there is no problem with that. Right? Just place it on your body, and then wherever you move, it will always record. So nothing to be blocked. You can block. So that's the pros of the IMU sensors. The cons is you have always the changing Earth magnetic field that I mentioned just now. So this will always affect. So it is always best to calibrate. Every time before you make a measurement, calibrate first, right? So calibrate. There's a program to calibrate, so that the measurements will align according to the current Earth magnetic field. And then you can start using. So the solution is by calibrating, right? And then I can say that it's also less resolution in terms of the body frames, right? And then because we are using it, if we compare this to the IMU to the vehicle motion capture, the IMU is more like a relative measurement. So let's say you have two. Let's say you have two IMUs. One on your upper arm, the other one on your lower arm. So if you want to measure the body frames, so it is based. You have to. So this motion over here is based on the position of the other sensor. So it's relative. Whereas if you use Vicon, it is absolute measurement, because those cameras are observing every point of that specific biomarkers. And it is also uncontrolled. So it is used in an uncontrolled environment. Let's say if you want to do experiment, you want to do a specific research, right? If you want to do a specific research, you need to control as many variables as possible, right? Because it is used outdoors, right? You have less control, and then you have so many variables. So it might not be that you need more processing if you want to apply these sensors in the outdoor environments. Okay. We are looking at this. I'm showing to you different perspective. If in vehicle motion capture, we are looking at specific motion capture. We look at knee, joints, angles, or rotation. And then if we use IMU, right, you need to map these IMU measurements to those of the vehicle motion capture system. And then usually when you talk about biomechanics, we're talking about the human body frame, right? But these IMU sensors, it's not only to look at the human body frames. It's not only for you to look at the entire body movement, right? So because it is you can apply this anywhere on parts of the body. You can on a different perspective, right? You can apply this as a single point measurement, right? To, let's say, for example, to measure local orientation. and then it is based, then the measurements you get is based on a signal, right? Let's say you place this on a racket, right? So you can swing the racket, and you can get the measurements of X, Y, and Z acceleration and gyroscope. Let's say when you swing the racket and then your racket hit the shuttlecock, right? So there will be changes of signal of the IMU, and then you will know that you can see some signal changes from swinging of the badminton racket to hitting the shuttlecock. There will be signal changes, and these signal changes you can extract features from the signal and apply machine learning, right? And then, like I said just now, instead of looking at the entire body frame, you can use IMU to focus on certain parts of the body. Let's say, for example, we have sports injury, right? You have sports injury. So you want to look at certain parts, you want to monitor only some parts, such as the leg, for example, maybe your you call it your knee, or your hip. I said your hip. You want to see how your hip moves after you have the injury, and then maybe some treatment, and then maybe post treatment, and then towards healing. Then you want to monitor. So you're looking at certain parts. Then this IMU is good for you. So instead of going, I mean, every time you want to look for to measure injury, you want to use a Vicon. It's not. It's a big setup. So which means that if you want to use a Vicon, usually you want to look at some specific measurements. Whereas for IMU, you can use that for daily measurements, monitoring, right? So it is an inclusive system device. Okay, I'm sharing with you some research application in sports. Okay, now we're going into sports. So let's say for archery, right? We're talking about outdoor. So in this manner that I've shown here. So it's not totally about the human body frame. So you can use IMU on its own, right? To for example, measure the postural body sway for archery. For badminton, you can apply that to the racket strokes, to measure racket strokes. For cycling, maybe you want to have two IMUs between, at the two ends of the joint to measure joint angle, or you can place it at the back to measure the rider lean, and also you can put it on the bicycle to measure the bicycle kinematics, right? Or you can also apply in the sports of springboard diving. Maybe you want to look at certain points of the sports activity. Let's say during takeoff during diving, springboard diving, right? Or during touchdown, you want to measure at certain angles. So which means here we're not looking at the entire. We're not recording the entire action of the sports. But it is more suitable if you want to look at specific motions and specific parts of your body. Okay. Right. I want to show you some specifications. So for IMUs, we have some parameters like degree of freedoms, DOF. So we can have a 6-axis accelerometer. Sorry, 6-axis IMU. So 6-axis means we have 3-axis accelerometer XYZ and 3-axis gyroscope, and then you can have 9-axis IMU devices, which will include another 3-axis of the magnetometer, and also sometimes there is a 10-axis IMU where you will also include the height altimeter. Right? Let's say for example the springboard diving, right? It involves the changes of height. So you can use the IMU which have the 10-axis feature. And then the measurements of the accelerometer, this is G. The measurement, the unit is in G. So you have a plus, minus, 2G gravity, 4G, 8G, and 16G. Right. For slow motions or for maybe walking, right? You can use 2G, right? But if you want to detect harder, strong movements like the racket hitting the shuttlecock, smash. So you want to have IMU which is able to measure at 16G, right? And then also for gyroscope, we have ranges with few range 250, 500, 1000, and 2000 degrees per second. So why we want to look at this full scale range? So it depends on the spots that you want to measure, right? So sometimes these devices might be too costly. It might cost you these IMU sensors. If you look at those the ones available on off the shelf in the market, it can measure up to 16G, but it costs you so much. It costs you quite a few thousands, and so it is not accessible to most spots, because it is it is costly, and then only a few people can have it, right? But if we were to look, if we were to consider, if we identify that our sports or training that we implement to our athletes, it is not like sports that require that so much high measurement of acceleration. Let's say for certain sports 4G is enough, right? Then you don't need to buy those sensors with 16G, right? So if you consider your sports to be not that high, not consistent of that high acceleration, then you can get these sensors, IMU sensors, with a more affordable price. So actually, it's not always you buy those most expensive ones. Of course, you can buy that lah, but that will be exclusive to certain sports. So what I'm suggesting here is that everyone can have access to these IMU sensors. So it depends on your creativity. You can apply to trainings. So to make these IMU sensors available to most coaches, so we need to look at how much acceleration and gyroscope measurements that you require for your training, right? Let's say for injury, right? For injury, when you are injured, you don't move that harsh, right? Or move that fast. So for injury, you don't need 16G measurement, right? 2G is enough, right? And if you look in the market, or if you outsource someone to design boards for you, right? Like this box over here, right? We do this in-house. So you say you want only 2G, so you can choose a cheaper ICs or sensors, and then you can have a more affordable IMU sensors for that specific application only, right? So then most of us would have access to these IMU sensors. Okay, we're almost going to 12. Okay, so when you design, let's say you can buy this IMU sensors. It's available off the market. You have many brands. You can buy mostly from international vendors lah, right? But usually when we design, what do we consider? So we want that these boards, these IMU sensors, when we design, to be put on the bodies of these athletes. We don't want them to realize that this board is on their body, right? On our side over here, we have tested this on several occasions, because during the early days is quite big lah. It's quite big. So the athlete doing the training, right? He keeps on looking, feeling. Oh, there's a sensor. There's a sensor. So which means when he noticed the sensor, right? So that disturbs his concentration on the sports training, right? So the best thing is, the best feature is that when we put the sensor on the athlete and let them go for their training, 30 minutes training, 60 minutes training, right? They would not realize that the sensor is there, right? So it should be lightweight, it should be small size. The battery should be long lasting, right? Of course, when you have bigger device, right? When you have bigger device, your device actually a big part of the sensor to have a long lasting recording is the battery, right? So if you have longer, if you have bigger battery, your sensor would last longer, right? But I think your IMU sensor will be big, right? It will be big, and when you wear that on the athlete, they will notice, right? And they will it will disturb the concentration of their training. So depends. It might be that you only want to record. Let's say, for example, you don't need to record for that long. You want to record only for the first few 20 minutes. So you don't need a large battery, right? So you can outsource. You can outsource those. Let's say, okay, for this training activity is only 10-20 minutes. So those engineers can devise you a smaller battery, right? So it is smaller, but will only last few minutes. But it is because it is small, therefore it is lightweight and it is unnoticeable. Okay, and then we also would require that your sensor to be wireless, because you might want to record the measurements of IMU together. Let's say with a camera, you have a camera, outdoor camera, normal camera, video camera, and then you want to record together with the IMU sensors. So you want to record it real time, and therefore the data are sent wirelessly, live, in live during the training, and then you can monitor that the signals live. So you would want a wireless one, or you would want the IMU to have a big storage, big memory storage. Let's say with an SD card. So you don't bother about sending the signals live to your computer, but you store that on the memory card after the training is finished. Then you call it extract the data to do some processing. Okay, pardon me. Okay, processing. Let's say you have to get your signals. So these signals, when you do the setup with coaches or technicians, technology who do, or engineers who do the setup together with coaches. So when you get those signals already, so on the engineer side or the technician side, when you get the signal, you can start to process your signal. Usually, this is the few processing that is done with these sensors. The first is low pass filter, passes only low frequencies, right? So it removes movements which are very strong or harsh. So low frequencies activities might include things like swing or sway, right? Let's say you swing your racket, or you want to measure your body swaying during your archery, right? So you do low pass filter and you will get that signal only. Or if you want to focus on activities that for example, like a hit or smash racket, then you do this high pass filtering. So these parameters have high frequencies. For example, when you have the entire signal during a recording, what you can do is you do this filtering. Let's say you want to count how many hits or how many smash or how many swings during the training. So if you can do the counting after you do the low pass filter, or you can do the counting after you do the high pass filter. And then we also have other processing like time domain subtraction to remove noises. And then from these signals, you can also do feature extraction. You can extract activities like just now, hit or smash, and then you can train these machine learning systems to identify hit or smash, right? Or certain specific activities, so that in future, when you have model this machine learning method, what you can do is for future recordings, the machine learning models will help you to count, let's say how many hit and smash automatically, right? So that will help the engineers or technicians to count. Okay. So usually for Imu measurements, we have RMS, accelerometer. You can do stride length. You can do stride velocity. For both velocity and length, you can usually you calculate the mean, max, and peak and things like that you can get a count of cadence, stance time, or jerk, or you count how many jerks, right? So if you look at here, it's not the common biomechanics that we know, where we measure based on the entire human body frame, right? So this is based on specific parameters only, right? So with IMU you can do that, right? So if you want to apply IMU in your sports, you can think about which part of the training that you give to your athletes that you want to measure, whether there's an improvement or whether there's a decrease in performance, like that. Right. So for analysis, we have tools like MATLAB to do the signal processing, feature extraction, and then I think among the most popular one, the Python right now. I think most engineers are exposed to Python, especially those young engineers. Right, you can apply machine learning easily right now. During my time, you have to apply machine learning by coding, entirely coding. But right now, it's just by calling functions in Python, you can do machine learning. So it is much more accessible right now. So there's also Python package called the GatePy. So this Python package can calculate single lumbar mounted. It measures the vertical acceleration. So with this, you can actually measure your gait before, after, or post treatment during an injury. So actually, if you look at the journals in the academia, many sports have been applied, like gait, Nordic walking, running, sprint, badminton, tennis, basketball, baseball, volleyball, right? So the thing here is, the question here is, how do we make these IMU sensors accessible by most coaches, right? So this is what we are doing here in ETM. Like for example, myself, I'm a team with my research lab. We call it the SWET lab, Sports Wearable Technology Lab. So we have in-house design of sensors that are very, very small. So the thing is, depends on coaches, what do they want to measure specifically. We can customize that for you, right? And what we want is we want to make these IMU sensors accessible by most coaches, right? It is not that, like I said just now, it is not that accurate. If you want an accurate analysis of biomechanics, yes, you can go for Vicon motion capture. But at least before you go for the high-end analysis, right? You have the accessible. You can access to lower-end sensors like this IMU sensors. You can, and then when you find something, when you want to go further, deeper in towards research, then you can move on to those using the vehicle motion capture for deeper analysis. So you can start using IMU sensors first. So instead of going to motion capture, the optoelectronic motion captures. Right. So I think that's all. That's until here for my presentation on this lecture series. So I welcome questions from the floor.
Thank you, Dr. Najib.
Yeah.
For the talk, you can see that IMU are integrated with sports learning because they are small and collect multiple of data, including acceleration, orientation, and direction. May I know that in-house sensor that UTM developed, is there any project using that sensor, Doc?
Okay. Actually, the one that we have here is not the first version. This is after some iterations, improvement. This is the fourth version. So now you get this small, right? It's around 1 cm by 3 cm, right? 1 cm by 3 cm, and the thickness is less than 1 cm, right? This is the fourth version. The earlier version is quite bulky. Yeah? It's quite bulky. So in terms of application on our side, we are applying. We have not done specific research yet on any research like badmintons, right? But we do have collaborators and research students which are applying right now lah. Like we also have other lecturers doing this. Applying these sensors for hockey research, which is Dr. Ami from UTM also.
All right. One more question from Mr. Lee Jinwei. Hi, Doctor. Would like to know viability of syncing EMG postplate to IMU sensor, especially takeoff velocity, acceleration, RFD, neuromuscular parameters.
Okay. Would like to know the viability of syncing. Okay. So this depends on how you develop the system lah, right? Of course, if you were to you can purchase, you can obtain these high-end systems, which you call it consists of those EMG force plates to IM sensors. But basically, through engineering knowledge, we can actually develop, and the viability comes here based on the design lah. So we call it if in terms of syncing. So I would say that if you want to sync multiple sensors, IMU together with force plates together with IMG, it is best to do it by wired instead of wireless. In another method to you can apply this is by sync by time lah. So which means that you need to attach all these sensors, and you need to design so that there's a button there's a single button which connects to all the sensors, and when all these sensors receive this sync button, it will start at the same right time lah. But actually, it will not be a problem of syncing, because these processors, the processors on these sensors, is functioning at speed of 20 megahertz. 20 megahertz. So I would say that is 1/20 of microseconds. So 1/20 of microseconds. If there's an error, right? The error would not be that significant. If your application is to measure the movements of humans, but if you want to measure the movements of, let's say, robotics, high-end robotics which is very, very fast, or you want to measure the movements of, let's say, missiles. They move very fast. Let's say, for example, missiles, you need guided missiles that follows targets. So they need to have a very, very high processing speed. So for that, you need a higher processing, we call it power. Let's say in terms of maybe gigahertz, right? But for motion, for human motion, you don't need that high processing speed. Okay.
Okay, Doctor. I think this the last question for today. Hi, Doctor. Thank you for the talk. What is the typical error, some estimate of joint angle calculation using IMU compared to motion analysis system, which is gold standard? Are error bigger with high compared to low acceleration resolution due to gyroscope cumulative drift?
Okay. The typical error would be around, let's say, if you are talking about degrees per second angle speed rotation, so it might be around plus minus 5 to 10 degrees. So it's quite big actually. That's why even though actually you can use IMU I'm saying that you can apply MU to do motion analysis like you want to do it in vehicle motion capture system, but the post-processing you need to do is very big in terms of you need to remove the noise, you need to reduce the error, you need to have algorithms to estimate, and then even the calibration process, you need to do several stages of calibration processes. You need to calibrate these sensors, IMU sensors, in terms of static calibration, dynamic calibration, and then need to do that a few times, and then you can get a very accurate, not so accurate but acceptable accuracy measurement of IMU if you want to compare that to the vehicle motion capture system. But like I said just now, using this IMU is not only about measuring the entire human body motion capture, right? You want to also, with this sensor, and you can actually measure other than that, like you want to measure how many kicks, how many steps, how many hits, right? Things like that lah. Or how many swings, how many sways that you do. So it's more suitable for you for this sensor, the IMU sensor, to measure single parameter. So if you want to apply the IMU to measure the knee angle, you need to have at least two motion sensor. Then you can measure knee angle, and both of these are subjected to errors, right? But like I said just now, if you are not everyone have access to the vehicle motion capture system, right? So why not use this first? This is more affordable. You can find it. You can even employ some engineers to do this for you, right? And then when you get these measurements, roughly you know what you want to do, and then you go for the higher end measurements using the the vehicle motion capture system. So you need to apply some strategy lah, right? Some strategy.
Okay, Dr. Najib, due to time constraint, I think we have to stop here. Thank you, audience, for the question. Should be there any further question, please contact our organizer through the email in the chat box. On behalf of ISN, I would like to thank TS Dr. Najib for your time and great sharing with us today. Maybe we can have another session with you or your team in the next lecture series. Thank you also to the audience for your attention. We hope you enjoyed and benefited from this session. Do keep in touch with us via our official website, Facebook, Instagram for updates on upcoming events. Stay safe, everyone. Have a nice day. Goodbye. Assalamualaikum, Doctor.
Salam. Thank you, Jose, and everyone.
Okay, thank you.